Okay, so this is section 10.4 for physics. This is the last section in chapter 10. We're going to talk about phase changes and what we call latent heat. Okay, so just as a little bit of review, these are things that you know already, so we're going to go through them really quick. We do have three states of matter: solid, liquid, and gas, and we call these phases of matter. And they differ based on the movement of their particles. So particles can move from one phase to the other. And you look at there we go. If you look at the diagram below, you can see that here they're kind of moving around. Here they're moving a little bit faster, and this one in particular is moving fast enough so that it can escape the liquid phase and turn into a gas. And here we have equilibrium. So that just means we have an equal number of particles leaving the liquid phase and going into the gas phase, as we have those coming from the gas and condensing back down into the liquid phase. When we have an equilibrium of that, molecules leaving and molecules entering, we call that equilibrium. Okay? All right. Let's move this up here so I can, come on. There we go. All right, the closed container on the left, and you're talking about the one that we just saw before, is partially filled with a liquid, and so a vacuum exists above the liquid. And then as the particles move faster, some of them do move faster than others. We talk about temperature. Temperature is just an average of their kinetic energy. So there's some particles that are moving really fast, and then there's others that aren't moving so fast. So the more energetic particles are able to escape the liquid and go into the vacuum, and then that's when they start to form a gas. When that particle leaves the liquid and goes into the space above, that makes it a gas. This process of particles escaping from a liquid until the vapor continues until the vapor is dense enough that a large number of gas particles are hitting the liquid and return to it. So when the number of those going back down into the liquid phase equals the numbers of them leaving the liquid phase, then we say that that system is in equilibrium. Okay, so let's go back to that picture and take a look at what we're talking about. So here we have particles just all in the liquid phase, and they're moving around. There's nothing up here. But some of these, if you notice the distance of their arrows, gives an indication of their kinetic energy. So some of them have a lot of kinetic energy, some of them just have a little bit. So those with a lot of kinetic energy have enough energy to punch through that liquid phase and go into the gas phase. And as more of them have that kinetic energy, more of them leave the liquid phase and go into the gas phase. When you have equal numbers going into the gas phase and then coming back through to the liquid phase. So now you've filled up this empty space here, this vacuum, and some of these particles, as they hit the liquid phase, they turn back into a liquid. They go back into the liquid phase because you just have tons of them up here, and that pressure is going to eventually cause some of them to go back into that liquid phase. And when you have equal numbers of those things happening at the same time, we call that equilibrium. Okay. So useful ways to characterize gas and liquid phases is with pressure. In general, you need to remember that pressure is the amount of force exerted on a given area. The amount of force exerted per unit of area. Okay? So if we go back to that diagram again, right here, in this particular container, we have more of these gas particles here. So that means they're going to be hitting the walls of that container and the top of that liquid with a higher pressure because they're going to have more force per unit of area. So if we increase that pressure, that's what's going to cause some of them to head back into the liquid phase. So we can describe or characterize gases and liquids with the term pressure. Just remember, pressure is the unit of force, or is the force per area. Okay, so there is our formula for pressure, force over area. Its units are newtons per meter squared. Okay, the symbol is going to be capital P, so make sure you're aware of that. All right. Shorthand name for units of pressure is a Pascal, and it's named for French scientist Pascal. 1 Pascal is 1 Newton per meter squared. Typical pressures are in the range of 1,000 pascals or 1 kilopascal. So atmospheric pressure, which is the pressure the atmosphere exerts on us, is 101 kilopascals or 14 pounds per square inch. Now, both of these are not our metric units of pressure. Those are going to be atmospheres and millimeters of mercury, which I'm sure we'll get to in just a minute. All right, the pressure of a gas in equilibrium with a liquid is referred to as the equilibrium vapor pressure. And the name kind of gives away the definition. Equilibrium vapor pressure is the pressure of a gas at equilibrium with the liquid. Equilibrium vapor pressure curve for water is shown it's going to be shown on the next slide. For each temperature, there's just one equilibrium vapor pressure. Just one pressure that creates a balance between the two phases, the gas and the liquid phase. So if we look, and here's our diagram. So here's our vapor pressure of water. So at 55 kilopascals, the temperature, the normal boiling point is going to be less than 100. So the normal boiling point, that's your equilibrium vapor pressure right there. At atmospheric pressure, it's around 101, so our normal boiling point is at 100. If we were at 200 kilopascals, it would be 120. Okay, so when we talk about equilibrium vapor pressure, normal boiling point is another way of saying that. Liquid boils at its boiling point, which is the temperature at which vapor pressure equals the external pressure. So in the previous slide, the atmospheric pressure corresponding to the boiling point of water at 100 degrees would be whatever that was. Yeah, atmospheric pressure, because that's when something boils, when the pressure on top of the liquid and the pressure underneath wind up being equal, and that pressure of the gas that's under the liquid is able to pop through, and that's when we say things begin to boil. The boiling point of water is less than 100 degrees Celsius on a mountaintop where the pressure is less. Okay, so remember from gas laws and such that pressure and temperature are directly related. So if we reduce the pressure, we're also going to reduce the temperature. That includes the boiling point. Boiling exceeds 100 degrees if your pressure is higher. So when you have an Instapot or a pressure cooker, they call it Instapot now, but a pressure cooker, what the science behind that is that you are increasing the pressure in that pot above atmospheric pressure so that the boiling point of that, whatever it is, water in there, the boiling point is going to not be 100 degrees Celsius, it's going to be something above 100 degrees Celsius. So your temperature inside that pot to get the water to boil or whatever is going to be much higher than 100. So that means if the temperature's higher, the food is going to cook faster. That's why your Instapot or your pressure cooker can cook an entire chicken in 20 minutes, whereas you'd have to do that for over an hour in an oven. Okay, so that's kind of the logic behind those things. You increase the pressure, you will increase the temperature at which something boils. And if you're increasing that temperature at which it boils, then you're going to have higher temperature inside there and it's going to cook faster. All right. So the process of particles leaving the liquid phase and going into the gas phase is called evaporation. And evaporation is actually a cooling process. So you need to know that. Evaporation is a cooling process. And the figure, this is showing that happening. So this is your skin, and this is a drop of sweat, which is mostly water. The higher speed molecules are able to leave the liquid phase and go into the gas phase. And that's going to reduce the temperature when it leaves that and goes into the gas phase, because it's going to have less pressure, which means a lower temperature. And that's going to cause the thermal energy then to be drawn out of the skin to balance that out. Because you're reducing the temperature here, your body is going to it's going to go, things move from hot to cold. So since you're reducing this temperature by this stuff evaporating, the heat, the thermal energy inside the body is going to be transferred outside the body and thus cool the body off. Okay. All right. The atmosphere of a planet or moon can also evaporate. In the case of an atmosphere, however, it is the force of gravity that has to be overcome. So the moon has a weaker gravitational field and is unable to maintain its atmosphere at all. So we have different levels of the atmosphere. And that atmosphere stays where it is because of our gravitational force. The moon has a much weaker gravitational force, so any atmosphere that it had just evaporated away. The speed of nitrogen molecules and oxygen molecules in our atmosphere is about 340 meters per second. So a molecule of gas on Earth does not have nearly the speed that it needs to overcome that force of gravity. The speed it would need to overcome the force of gravity and escape and move away would be 11,200 meters per second. And they're not going that fast, so they can't overcome our force of gravity and escape. So there are situations where heating a substance does not always increase the temperature of that substance. So let's try and think, pause the video, try and think of some times when heating something doesn't increase the temperature. Okay, we did learn this last year in chemistry, so think back to that. All right, so when two phases coexist, the temperature remains the same even if we add heat. So you need to make sure you have that written down. If two phases coexist together, so if we have a liquid and a gas together, or a liquid and a solid together, then at those places, even if we add more thermal energy or add more heat, the temperature is going to remain the same. So let's think about an ice cube. An ice cube is like -10 degrees Celsius. We add heat to the ice cube and it increases its temperature until it reaches 0 degrees Celsius. At 0 degrees Celsius, additional thermal energy does not cause an additional increase in temperature. So what it does instead is that energy is going into converting the ice solid to water, a liquid. Okay, so at phase changes, so we're talking about melting and freezing, we're talking about boiling and condensation. At those temperatures, or at those places, any additional thermal energy does not go to increase the temperature. It goes to convert, to break the bonds that are holding those molecules together and convert a solid into a liquid or a liquid into a gas. As long as the ice remains in the cup, the water and ice are in equilibrium. Both the ice and the water will stay at 0 degrees Celsius. So at that phase change, the temperature is going to stay the same for both of those things. So there'd be no change in temperature. During the conversion process from one phase to another, the temperature stays the same. The thermal energy required to change 1 kilogram of a substance from one phase to another is called the latent heat. So you need to know that definition. Latent heat, capital L, is the thermal energy necessary to change 1 kilogram of a substance from one phase to another. Thermal energy required to change 1 kilogram from one phase to another is what we call latent heat. Here is our formula for determining the amount of heat that's required to do that. So the heat required to change from one phase to another is Q times M capital L, where capital L is the latent heat. It depends on which phases are present. So there is a latent heat for freezing. So the heat needed to freeze a liquid into a solid is the latent heat of fusion. So watch out for that particular abbreviation. The heat needed to vaporize something or boil it is the latent heat of vaporization. And the heat needed to sublime something is the latent heat of sublimation. So you need to know those definitions and those abbreviations. There's some values, some sample values of latent heat of fusion and latent heat of vaporization for different materials. All right, this should look somewhat familiar from chemistry. This is we called it a heating curve. It's still a heating curve in here too, but the temperature of a substance in response to heating is known as its heating curve. Okay. Figure below shows the heating curve for 1 kilogram of water at negative 20 degrees Celsius. So you have the slanted lines, and that's where if you increase the temperature, if you add more heat, you're actually increasing the temperature. So these formulas would be Q equals MC delta T. And then at the flat portions, we have phase diagrams going on. So that's Q equals ML, L for the latent heat. So this would be the heat of fusion is equal to the mass times the latent heat of fusion. Heat of vaporization is equal to M times the latent heat of vaporization. And the diagonal lines are always going to be Q equals MC delta T. The curve shows the temperature of water as the thermal energy is added or removed. Notice that the temperature remains constant when the system is changing from one phase to the other. It's a flat line. So whenever you see that flat line, that lets you know you either have freezing / melting or you have boiling / condensation. All right, and then there are lots of problems that we're going to work with these. Now, the tricky part to these problems is when you have a problem, you're going to need to be able to pick out where is that latent heat of vaporization, where is that latent heat of fusion. So for example, if the problem says the temperature changes from negative 20 up to, and then goes up to 150, okay? So you can't just use Q equals MC delta T and your change in temperature is negative 20 is 150 minus a negative 20 because it's always final minus initial. You can't do that because in that process you have melting going on and boiling both. So you have to account for those heats as well because when we put in heat at the freezing point or the melting point, we're not changing the temperature, but we're still adding heat. Same with the boiling point. We're not changing temperature, but we're still adding heat. So we have to account for those phase changes as well. So it would be Q equals MC delta T, and that's going to take us from negative 20 up to 0, and then you'd have QF equals MLF for the 0 mark. Then you would have Q again, MC delta T, that's going to go from the 0 up to the 100, and then you would have Q vaporization, which is MLV at the 100, and then you would have another Q equals MC delta T for the 100 up to 150. Whoa, I want to go crazy. Okay, and then you would wind up having to add all those heats together to get the total amount of heat that was transferred from that negative 20 degrees Celsius up to 150 degrees. Okay, so those are places where it's really easy to mess up, because you just think, oh, well, it's two changing temperatures, boom, boom, I'm done. No, you have to consider if there's a phase change going on, you have to consider that latent heat of vaporization or latent heat of fusion. Okay, it looks like that is the end of, that is the end of chapter 10. So if you have any questions about these, just bring them to class and we'll go over them.